Hi everybody, and welcome to our module on pulmonary physiology. Let's start by talking about lung volumes. So as you breathe, you inhale and you exhale, and the volume in the lungs changes over time. And in pulmonary physiology, there are 4 important lung volumes that you need to know. So let's go through them right now. On this graph, time is along the x-axis as a person is breathing, and the volume in the lungs is along the y-axis. And the red line is going up and down as the person inhales and exhales. First important volume is called the tidal volume, the TV right here. And this is the volume of air that moves in and out with quiet breathing. Quiet breathing is the automatic breathing you do when you're not thinking about it, when you're not trying to apply force to inhale or exhale more forcefully. So you can see that the red line is going up and down here with this small volume of air going in and out. That is the tidal volume. If you were to exhale as hard as possible and push as much air out of your lungs as you could, you would not only exhale the normal tidal volume, but you would exhale an extra volume called the expiratory reserve volume. Along that same thinking, if you were to inhale as forcefully as you could and try to fill your lungs completely, you would not only inhale the tidal volume, but you would inhale an extra volume of air here, and this is called the inspiratory reserve volume. And then the fourth volume is this one down at the bottom, the residual volume. No matter how hard you try to blow air out of your lungs, you never get below this number right here, and that's because there is a residual amount of air, this is the residual volume of air, that will always be in your lungs, and you cannot blow it out no matter how hard you try. And I've summarized these points on this slide. You need to understand what each of these volumes represent. The tidal volume is the air that goes in and out with each quiet breath. The expiratory reserve volume is the extra air that you can push out with force, but remember, you still would have that residual volume remaining in the lungs. The inspiratory reserve volume is the extra air that can be drawn in with force beyond the tidal volume. This is where the lungs are filled to capacity. And then finally, that residual volume is the air that can't be blown out no matter how hard you try. In pulmonary physiology, we also talk a lot about lung capacities. A capacity is a sum of 2 or more volumes. The first capacity that's important is the total lung capacity. This is the sum of all the volumes. So if you look at this graph now, which I've expanded to show the capacities, this is the total lung capacity, and that's that number of about 6 liters that I told you before. This number includes the residual volume, the expiratory and inspiratory reserve volumes, and the tidal volume. The inspiratory capacity is the most air that you can inspire, so this is the tidal volume, the air that you would inspire with a quiet breath, plus the inspiratory reserve volume, the air that you would inspire if you put more force into it. Along those same lines, the vital capacity is like the reverse of the inspiratory capacity. This is the most air that you can exhale. So this is all the volumes in the lungs except the residual volume. So it's the tidal volume plus the inspiratory reserve plus the expiratory reserve. And I've shown all these capacities on this slide over here. This is the inspiratory capacity here. This is the vital capacity here, and the total lung capacity is over here. And the last lung capacity is the functional residual capacity, and this is the most important one for you to understand. This is the residual volume that's left in the lungs after quiet expiration. So if you look on this graph, at this point right here, this is where the lungs come to rest after a cycle of inhalation and exhalation. And there's a very important reason why the lungs come to rest at this volume, which we'll talk about later. That's the point where the forces in the lungs are balanced, and that's why the lungs like to rest there. But in terms of volume, the functional residual capacity is the residual volume plus the expiratory reserve. It's these 2 volumes right here. And like I said, it's the volume when the system is relaxed, and as we'll talk about later, it's an equilibrium position where the chest wall is pulling out and the lungs are pulling in and the forces are balanced. So now let's move from lung volumes to lung pressures. Just like the volume of air in the lungs goes up and down as you breathe, so also does the pressure in the lungs. It goes up and down during different points of the respiratory cycle. So atmospheric pressure, you may know, is 760 millimeters of mercury, but in pulmonary physiology we just call it 0. This just makes the numbers and the math more simple. So the first important pressure is the alveolar pressure. This is the pressure within the alveoli, as the name implies. The second important pressure is the intrapleural pressure. This is the pressure in the pleural space. The pleural space is the space between the lungs and the chest wall. And then the third important pressure, which is probably the most important one, is the transpulmonary pressure. This is the difference between the alveolar pressure and the intrapleural pressure. I'll show you some numbers about this in just a minute. But the reason this is such an important pressure is because this is the pressure across the walls of the alveoli, and this is necessary to keep the alveoli open. If the transpulmonary pressure is too low, the alveoli will collapse and gas exchange won't occur. So here's a drawing that I'll refer back to a number of times in this video. So we have air flowing into an alveolus here. The pressure in here is the alveolar pressure. Outside of the alveoli, we have the intrapleural space, which is surrounded by the chest wall. And so the transpulmonary pressure, the TPP here, is the difference between the alveolar pressure and the pressure in the intrapleural space. It's alveolar pressure minus intrapleural pressure. So let's look at two examples of pressures in the lungs and talk about what happens to the transpulmonary pressure. So on the left side, we have a pressure of +5 inside the alveoli, and we have a pressure of +5 in the intrapleural space. The transpulmonary pressure, therefore, is 5 minus 5, which is 0, and this would be bad. If this actually happened, your lungs would collapse. On the right side, we have a situation that often occurs during many points in the respiratory cycle. The alveolar pressure is 0, and the pressure in the intrapleural space is negative at -5. If you do the math, the transpulmonary pressure, therefore, is 0 minus -5, which is +5, and this is good. We have a positive pressure of 5 millimeters of mercury, keeping the alveoli open. And this is one of the points of pulmonary physiology that's confusing for a lot of students. You have a negative pressure out here in the intrapleural space, but when you do the math, that creates a positive transpulmonary pressure. That's just the way the math works out, and it makes sense. This negative pressure here in the intrapleural space is basically like a vacuum. It's sucking the walls of the alveoli open and creating a positive transpulmonary pressure that prevents alveolar collapse. So let's talk in a little bit more detail about the intrapleural pressure. As I mentioned before, this pressure is negative at all times during normal, quiet breathing. The reason for this is because the alveoli in the lungs want to collapse. They want to pull inward and recoil, and they need an outward force to keep the walls open. In contrast, the chest walls want to expand. Your ribs and the muscles of your chest wall, they want to move outward. They want to spring outward. And for this reason, they create a negative pressure in the pleural space, and that negative pressure sucks the alveoli open. It creates a positive pressure across the walls of the alveoli, and that's what keeps them from collapsing. And just to emphasize how important the transpulmonary pressure is, let's briefly talk about a pneumothorax. So in a pneumothorax, there is a hole in the lungs, and that changes the intrapleural pressure. Shown on the slide right now is a normal lung setup. We've got a pressure of 0 in the alveoli. We've got a pressure of -5 in the intrapleural space, and that's creating a transpulmonary pressure of +5 to keep the alveoli open. In a pneumothorax, the pressure in the intrapleural space becomes 0. That's because there's a hole in the lungs allowing the atmosphere to connect to the pleural space. When this happens, the transpulmonary pressure becomes 0, and that means that the lungs collapse. There's no force to keep the alveoli open, and they want to collapse, so they will collapse, and that's what happens in a pneumothorax. And here's a chest x-ray of a patient with a pneumothorax. These are the lungs here on the right side. They have entirely collapsed. They are not filling this space in the thorax as they should. A pneumothorax has a hole in the lungs, and it turns the intrapleural pressure to 0, and that makes the lungs collapse. A classic example of the importance of transpulmonary pressure. So one reason that pressure inside the lungs is important is because it keeps the alveoli open. But the other reason lung pressures are important are because they drive airflow. So let's talk about that now. So imagine that the pressure in the atmosphere was 0, which it always is, and imagine that the pressure in the alveoli was also 0. This would be a delta, a difference in pressure of 0, and anytime there's no difference in pressure, there will be no airflow. Now let's imagine the pressure in the alveoli changes to +5. We still have a pressure of 0 in the atmosphere, so now we have a delta of +5, and air is always going to flow from a high pressure to a low pressure, so this means we're going to get flow out of the lungs. As we'll talk about in a minute, this is what happens in many points in the respiratory cycle. The alveolar pressure becomes positive, and that drives air out of the lungs. Conversely, let's imagine if we had a pressure in the alveoli of -5. This happens also during some points in the respiratory cycle. Now we once again have a difference of +5, but this time the flow is going to be inward because the pressure here is 0, which is higher. The pressure here is -5, which is lower, and air always flows from a higher to a lower pressure, which will be into the lungs. So now that we understand that, let's go through the respiratory cycle and talk about how the pressures inside the lungs change. So once again, we're going to use the diagram I've shown on the left here. We've got air flowing into the alveolus. We've got the intrapleural space here and the chest wall here. And we begin in the resting state. And the resting state in a quiet breathing cycle is with a pressure of 0 in the alveolus, meaning it's at equilibrium with the atmosphere, and a pressure in the intrapleural space of -5. That's the resting pressure in the pleural space. And that is creating a pressure of +5 for transpulmonary pressure, which is just enough to keep the alveoli open and not collapsing, but not enough to expand the alveoli. So airflow and pressure changes during quiet breathing can be a confusing concept. So before I get into the specific numbers, let me give you the big picture. In the resting state, the intrapleural pressure is negative at about -5. And as we've been discussing, this is just enough suction pressure, just enough negative pressure to keep the alveoli open. When you contract your diaphragm, the chest wall expands and the intrapleural pressure becomes more negative. It can get as negative as -8. This is going to add additional suction force onto the alveoli, and it's going to create a negative pressure inside the alveoli. And when the pressure becomes negative in the alveoli, air is going to flow in, because remember, atmospheric pressure is 0, so if you have a negative pressure in the alveoli, air is going to flow in. So the big picture here is that airflow into the lungs is entirely driven by a change in the intrapleural pressure, and what's really confusing is the change is from negative to more negative. But don't get thrown by the numbers. The idea is simple. You're applying additional suction force, creating a negative pressure in the alveoli, and drawing air into the lungs. When you exhale, you relax your diaphragm and the intrapleural pressure becomes less negative. It goes back to -5. This is going to cause the reverse to happen. The pressure in the alveoli is going to become positive, and this is going to push air out. Now, this is confusing that it's becoming positive when there's a negative pressure in the pleural space, but the idea is simple. By going from -8 to -5, you're actually adding pressure to the alveoli. That is going to create a positive pressure in the alveolus and push air out. So the big picture here is that everything in terms of airflow in and out of the lungs is driven by changes in the intrapleural pressure caused by contraction and relaxation of the diaphragm. What's confusing is the numbers. It goes from negative to more negative to less negative, but don't let that throw you. The idea is very simple. You're creating more suction force to draw air in, or creating less suction force to push air out. So I've summarized these points here. When you inhale, the intrapleural pressure becomes more negative. This is going to cause the pressure in the alveoli to become negative, and that's going to draw air into the lungs. When you exhale and you relax your diaphragm, the intrapleural pressure becomes less negative. This is going to cause alveolar pressure to become positive. I'll show you a picture of this in a minute. And this is going to cause air to flow out of the lungs. So now let's look in detail at what happens during inhalation. We begin in our resting state. The intrapleural pressure is -5, the alveolar pressure is 0, and the transpulmonary pressure is +5. Then we contract our diaphragm and the chest wall expands, and the intrapleural pressure becomes more negative at -6.5. So basically what's happening here is by going from -5 to -6.5, we've given the lungs a force of 1.5 that they can work with to drive airflow. One of that 1.5 is going to go into the alveoli. The pressure here will become -1, and we've got an atmospheric pressure of 0, and air always flows from high to low pressure, so air will begin to flow into the lungs. We're also going to use 0.5 of that 1.5 of force to increase the transpulmonary pressure. This is going to cause the lungs to begin to expand. So just what you expect to happen in inhalation is happening here. Air is flowing into the lungs and the lungs are expanding. But it's all being driven by a change in the intrapleural pressure. That's the only thing the body can change. And that intrapleural pressure has gone from -5 to -6.5. This is confusing because it's going from negative to more negative, but the idea is simple. We're just increasing the amount of force that we can use to draw air into the lungs and expand the lungs. What happens at the end of inhalation is shown here. So as air flows into the lungs, it begins to fill the lungs and the pressure starts to go up. So it stops being -1 and it goes up to 0. And once it gets to 0, airflow is going to stop. At the end of inhalation, we've made the intrapleural pressure even more negative, all the way to -0.8. This has made the transpulmonary pressure really high at +0.8, but at this point we're going to stop contracting our diaphragm and begin to relax it. So this is where the process is going to end. We're going to end with 0 pressure in the alveoli, no airflow, and then we're going to start to reverse the process. So here's what happens with exhalation. We take that -8 intrapleural pressure and we make it less negative. We go down to -6.5. Once again, this means we're changing the forces in the lungs by 1.5. So what are we going to do with that change? Well, some of that force is going to be transmitted to the alveoli and the pressure there will become +1. And since atmospheric pressure is 0, this is going to cause air to flow out of the lungs. And then the transpulmonary pressure, which was +8, is going to decrease to +7.5. This is going to cause the lungs to shrink. So all the things that would logically happen with exhalation are happening. Air is flowing out of the lungs and the lungs are shrinking. What's confusing is the numbers, because this is all being driven by a change in intrapleural pressure from -8 to -6.5 and a change in transpulmonary pressure from +8 to +7.5. But keep your eye on the big picture. What we're doing is we're decreasing the suction force on the lungs that's causing the lungs to shrink and that's causing air to flow out. And here's what happens at the end of exhalation. That intrapleural pressure becomes less negative. It goes from -6.5 to -5. The pressure in the alveoli is going to fall back to 0 because air is leaving the alveoli. When it becomes 0, there's no more airflow, and we're back to a resting state with a transpulmonary pressure of +5. Once again, all this has been driven by changing the intrapleural pressure from more negative to less negative. So everything that I've just talked about in terms of volumes and pressures is shown on this graph. This is a classic pulmonary physiology graph showing the change in pressure and volume inside the lungs during quiet tidal breathing. If you understand everything on this graph, you can answer lots and lots of pulmonary physiology questions in step 1. So at the top we have the line shown in blue here. This is the volume of air in the lungs. We start at the FRC. Remember, that's where you always start and end during quiet breathing. That's the point where the lungs are in equilibrium. You begin to inhale and the volume in the lungs goes up. You inhale about a half liter with each quiet breath, and then you begin to exhale and the volume goes back down to the FRC. This should be very easy to understand. Volume is just going up and down during a respiratory cycle. In the middle of the graph is the change in alveolar pressure during a quiet breathing cycle. So remember, we always begin at atmospheric pressure of 0. That's where we start a quiet breathing cycle. The pressure in the alveoli becomes negative, and that draws air into the lungs, and then the pressure begins to rise and goes back up to 0. It's at 0 at the beginning of inhalation and at the end of inhalation. Then we begin to exhale. The pressure in the alveoli becomes positive. This pushes air out of the lungs, and then we come back to 0 once again. So in terms of alveolar pressure, we begin at 0. We're at 0 in the middle of a cycle, and we're at 0 at the end of a cycle. During inhalation, the pressure becomes negative, and during exhalation, it becomes positive. And then finally, at the bottom is the intrapleural pressure, and this is the one that's often tricky to understand, so make sure you get this. The intrapleural pressure is always negative. It begins at about -5. At the end of inhalation, it's down to about -8, and then it goes back up to -5. So the pressure in the pleural space is always negative during quiet breathing, whereas the pressure in the alveoli is fluctuating from 0 to negative to 0 to positive. Once again, make sure you understand this graph on the screen. This is the basis for lots and lots of Step 1 questions. So up to this point in this video, we've talked about lung volumes and we've talked about lung pressures. And what we're going to do now is talk about volumes and pressures together because the two are related. When the volume of air in the lungs changes, so does the pressure and vice versa. So years ago, physiologists began studying lungs, and they did this by removing the lungs from the body, either of cadavers or animals. And what they did was they applied pressure to the lungs and they watched how the volume changes. And they found a relationship like what is shown in this slide. When there is no pressure inside the airways, the lungs have no volume. They're completely collapsed, just like a balloon with no air inside of it. As you begin to apply pressure to the walls of the lungs begin to expand, and the y-axis here is volume. And so you see that the volume goes up until it reaches some maximal value. This is a fairly straightforward relationship to understand, and it's what happens if you apply pressure to the walls of the lungs outside the body. Then physiologists began to study the pressure-volume relationship of the lungs inside the chest cavity when they're being used by a living human being. And they found the relationship shown on the slide here. And as you can see, it's very different from the relationship we saw on the last slide for the lungs outside the body. So for a long time, people struggled to explain why the pressure-volume relationship of the lungs is different when the lungs are outside the body compared to when they're inside the body. Notice that when the lungs are inside the body, even when there's no pressure in the airways, there is still a volume. In other words, the lungs never completely collapse the way they do when there's no airway pressure outside the body. Also notice in the green line that as you apply more pressure, you do add volume to the lungs, but not as much as if the lungs were outside the body. You can also apply a negative pressure and begin to shrink the lungs. So people tried to understand this for a long time, and eventually they figured it out. The reason that the lungs behave differently in terms of the relationship between pressure and volume inside the body is because the lungs are not there all by themselves. The lungs are also affected by the chest wall, and the chest wall has its own pressure-volume relationship, and that affects the volume of the lungs. When the lungs are by themselves, there's nothing outside of them that modifies their volume, but when the lungs are in the body, the chest wall is outside, applying that negative suction pressure we talked about before, and that influences the volume of air in the lungs. So let's look at the chest wall volume pressure relationship all by itself. Like I told you before, if this is a wall of your chest, and your lungs are here in the middle, the chest wall wants to spring outward, and so that creates a negative suction type pressure in here that tends to open up the lungs and increase the volume. So if 0 pressure were applied to the walls of the chest, there would still be some volume here because they naturally want to spring outward. And you can apply positive pressure and increase that volume. You can apply negative pressure and decrease that volume. But the key point is that at a pressure of 0 on the chest walls, they still have a volume, and that's very different from the lungs. The lungs by themselves at a pressure of 0 have no volume. So now let's look at the three curves together. The blue curve is the lungs, the red is the chest wall, and the green is for the respiratory system as a whole. And what you can see is when there's no pressure inside the airways, the respiratory system as a whole is going to have a volume right here on the y-axis, and that volume is the FRC that we talked about earlier. What's happening at this point is at this volume, the tendency of the chest wall to expand the lungs, in other words, to apply negative suction and make the lung volume bigger, is perfectly balanced by the tendency of the lungs to collapse and want to have no volume inside of them. So those pressures between the lungs and the chest wall are balanced right here at the FRC, And that's why at the end of a quiet breath, you settle at that point where everything is in equilibrium. So let's review the concept of the functional residual capacity once again. We talked about this earlier. When this volume of air is in the lungs, the tendency of the lungs to collapse inward is balanced perfectly by the tendency of the chest to spring outwards. This is the volume of the lungs where they come to rest after quiet exhalation. And at this point, the pressure inside the system will be zero. There's no increase or decrease in pressure from push-pull of the lungs or the chest wall, and the pressure inside the lungs is zero, which, as we talked about before, is atmospheric pressure. Lung compliance is the change in volume you get for a given change in pressure. I've shown this equation here. And we talk about compliance in lots of areas of human physiology. We talk about compliance of the left ventricle of the heart, compliance of blood vessels, and we're talking about the same thing here. This is a measurement of how stiff the lungs are. It says if you apply a given pressure change, how much does the volume change? If the lungs are very compliant, it takes a small amount of diaphragm effort to generate just a small amount of pressure and you'll get a large volume change. So compliant lungs have an easy time moving air in and out because they easily expand and contract. Non-compliant lungs are stiff. You need to apply a large amount of effort from the diaphragm and a big pressure change just to get a small volume change because the lungs are stiff. And in non-compliant lungs, it's hard to move air in and out. And there are many disease processes where the compliance in the lungs changes, either where they become more compliant or less compliant. And this is related to the relationship between volume and pressure that we've been talking about on the last few slides. So let's talk about how changes in lung compliance change the shape of the pressure-volume relationship of the lung. Here's that blue line for a normal lung and the pressure-volume relationship when it's outside of the body. If the lung becomes non-compliant, in other words, if it becomes stiffer and has a decreased compliance, it will begin to look like this red line. Notice that when you apply airway pressure to the red line, you get less of a volume change compared to the blue line. It's because it is a non-compliant or stiff lung. And now let's talk about what would happen to the pressure-volume relationship of the entire respiratory system as a whole if we had a change in lung compliance. So here's the graph we looked at earlier. The green line shows the pressure-volume relationship of the respiratory system as a whole. And this point right here is the FRC, where the lungs come to rest after a quiet breath. If we had a change in lung compliance, the lung curve would look something like this. When we do this, it lowers the FRC, and that is a huge and high yield point for you to understand. Anytime we have a change in lung compliance, so we move from the blue line to the dashed blue line, our equilibrium point where the chest wall is balanced with the lungs is going to be at a lower value. So patients who have diseases where their lungs become stiff and become non-compliant will have a lower FRC. In contrast, patients who have diseases where their lungs become more compliant will have an increase in the FRC. So decreased lung compliance occurs in some of the disorders I've listed here: pneumonia, pulmonary edema, pulmonary fibrosis, and in all of these conditions there is a decrease in the FRC. Super high yield to know this for pulmonary physiology questions on step 1. At the bottom of the slide are some things associated with increased lung compliance. Patients who have emphysema have floppy lungs and the lung compliance goes up. As we age, the compliance of the lungs go up. And the presence of surfactant makes the compliance of the lungs go up. So babies with neonatal respiratory distress syndrome who are missing surfactant are going to have stiff lungs. So if you have these things present, if you have emphysema or you're older or you have lots of surfactant in your lungs, that's going to increase the compliance and that will raise the FRC. And the fact that emphysema is associated with increased FRC is what leads to the barrel chest. This is something that you can appreciate just by looking at patients who have emphysema. Emphysema causes the lung compliance to increase. As I showed you before, that raises the FRC, so these patients have more volumes of air in their chest at all times. As a result, over time, their chest begins to expand, so instead of looking normal like this guy, they have a barrel chest right here. Everything you see here is caused by an increase in lung compliance and an increase in the FRC, all tied in to those pressure-volume relationships we've gone through in the last few slides. Now let's talk about forced exhalation. When you use all your muscles to push air out of your lungs as hard and as quickly as possible, the physiology of this process of forced exhalation is different than the physiology we've been talking about for normal quiet breathing. During forced exhalation, the pleural pressure becomes positive. This is going to compress the airway and put pressure on the alveoli and generate positive pressure in the airway, much higher than what you get during normal quiet breathing. And this is going to push air out and air is going to flow from the airways. So let's take a look at this alveolus I've drawn on the screen here. What happens during a forced exhalation is that the pleural pressure becomes positive. So remember I told you before, during normal quiet breathing it's always negative, but you can make it positive if you try to push air out of your lungs as hard as possible. So let's imagine that we create a pressure of positive 20 in the pleural space. What that's going to do to the pressure in the alveolus is make it even higher than that. It's going to be about plus 35. The reason it's higher is because not only do you have the plus 20 of the pleural pressure, but remember the lungs want to collapse in on themselves. That's called elastic recoil. So that pressure is added additionally, and therefore you get a very high pressure in the alveolus like plus 35. And remember that atmospheric pressure is 0, so now you have a very large gradient of 35 millimeters of mercury driving airflow out of the lungs, and that's why you're going to get a vigorous forced exhalation. So you might be wondering, if the pleural pressure becomes positive, why doesn't it collapse the lungs? So let's talk about that now. This involves an important pulmonary physiology concept called the equal pressure point. So let's look at this alveolus I've drawn at the bottom of the screen. We're engaging in a forced exhalation. The pleural pressure is positive at plus 20, and the alveolar pressure is even more positive at plus 35. And out here, the atmospheric pressure is 0. Now the pressure does not go from 35 to 0 all in one step. The pressure slowly drops as you get from deep within the lungs inside the alveoli all the way out to the atmosphere. So the pressure might drop, for example, to 25 at some point, and then at some point to 20. This point 20 is called the equal pressure point because now the pressure inside the lungs is equal to the pleural pressure. Once you go beyond the equal pressure point, the pressure inside the respiratory system is lower than the pleural pressure, and this is where the lungs would collapse, but that doesn't happen. And the reason for this is because in healthy people, this point beyond the equal pressure point occurs within the cartilaginous airway. So in the video on pulmonary anatomy, I talked about how some portions of the airway have cartilage and some do not. In healthy people, the equal pressure point occurs within the cartilaginous airways, and therefore the pleural pressure cannot cause collapse. So I've summarized these points on this slide. The equal pressure point is the point where pleural pressure equals the airway pressure. Beyond this point, the airway collapses, but in healthy lungs, the equal pressure point occurs in the cartilaginous airways, and therefore airway collapse does not happen. Here's a slide that I go through in detail in the video on pulmonary anatomy. It shows the respiratory tree all the way from the trachea through the bronchi and bronchioles all the way down to the alveolar sacs. And as shown on this slide, cartilage is only present in the early portions of the airway. There's cartilage present in the bronchi and in the trachea, but there is no cartilage in the bronchioles on down to the alveolar sacs. So in healthy lungs, the equal pressure point occurs somewhere above the bronchioles. It occurs somewhere in the bronchi. These bronchi have cartilage, and therefore they don't collapse even when the pleural pressure becomes higher than the airway pressure. If the equal pressure point were to occur here in the bronchioles where there is no cartilage, that would be bad, because without cartilage the airways can collapse if the pleural pressure becomes higher than the airway pressure. In patients with diseased lungs, however, the equal pressure point moves towards the alveoli, and therefore it can lead to airway compression. Let's look again at the bottom of the slide here. So let's imagine that we have a pressure of plus 20 again during forced exhalation. And now let's imagine that the equal pressure point has moved this way towards the alveolus. Now we reach a situation where we've got higher pleural pressure than airway pressure outside of the cartilaginous airways, and that's going to lead to airway collapse. This can happen in patients who have airway obstruction, like from bronchitis. We'll talk about that in a minute, but the pressure drops more rapidly there, so it goes from 35 to 0 more quickly, and therefore the equal pressure point occurs closer to the alveoli. This can also happen in emphysema because there's a lack of elastic recoil. So when this happens, when the equal pressure point moves towards the alveolus, it can be reached in the thin-walled bronchioles that don't have cartilage, and the result is airway collapse, obstruction to airflow, and air trapping, all of which are features of lung diseases like bronchitis and emphysema. So here's what happens in emphysema shown at the top of the screen. There's loss of elastic recoil. So when you generate that pleural pressure of plus 20, instead of getting plus 35 in the alveolus, you only get plus 25. That pressure is going to drop quickly and reach a value lower than the pleural pressure at some point before the cartilaginous airways. In bronchitis, what happens is there's more pressure drop compared to normal because of obstruction to airflow. So let's look at this example of plus 20 in the pleural space. We still have our elastic recoil intact, so we generate a pressure of plus 35 in the alveolus. But because the walls of the bronchioles and the bronchi are inflamed, there's more pressure drop as airflow moves out of the lungs. So instead of going to plus 20 and plus 15 at a point in the cartilaginous airways, we reach that point early, and therefore we have collapse of the lungs. And the key point here, and what they want you to know for your board exams, is that in these disorders, the equal pressure point moves towards the alveolus, and that's what causes it to be reached when you are outside of the cartilaginous airways. So patients with COPD have this problem of airway collapse when they breathe forcefully, and so they engage in certain behaviors to prevent airway collapse. The first thing they do is they slowly exhale. This prevents the pleural pressure from rising significantly, because if they breathed more vigorously, the pressure would rise and the airways would collapse. So by doing a gentle, slow exhale, those pleural pressures never get so high that they can collapse the lungs. The second thing they do is they purse their lips. Whenever you purse the lips, you create an obstruction to airflow and pressure builds up behind that obstruction. So pursing the lips is going to increase the airway and the alveolar pressure, and this is also going to prevent collapse. The last topic for this video is hysteresis. Hysteresis refers to the dependence of a physical property on its history. So for example, some substances have the same mass and volume no matter when you measure them, but there are other substances where the mass or volume changes depending on what was happening before you measured those values. And this is true of many things in science, but it's also true of the compliance of the lungs. So if you generate a pressure-volume curve for inhalation and exhalation of the lungs, they do not look the same. If you look down at the graph at the bottom of the screen, the inspiration curve looks like this and the exhalation curve looks like this. So even though it's the same lungs, the pressure-volume loop is different depending on whether the patient just inhaled or just exhaled. And since the slope of the pressure-volume curve is the compliance, we say that there is different compliance within the lungs during exhalation and inspiration, and that is the property of hysteresis. So what they want you to know for step 1 is that the pressure-volume hysteresis in the lungs is caused by surface tension. When you inspire, you start with the lungs at their smallest volume, and the molecules are very close together and there's a strong surface tension. So you have to exert a lot of force to break up that surface tension. As a result, you don't get the same change in volume you would otherwise. Expiration, on the other hand, begins at high lung volumes. The intermolecular forces are low, and therefore you get a big change in volume for a change in pressure. So if you look at this curve at the bottom right side of the screen here, let's look at inspiration first. When you begin to inspire, the molecules are close together. So even though you're applying a lot of pressure, you're really not getting much change in volume. In contrast, when you expire, all of those molecules are far apart, the intermolecular forces are low, and therefore as the pressure begins to fall, you get a big drop in volume. And that's why these two curves are different. And that's all you need to know about hysteresis for step 1. And that concludes our video on pulmonary physiology.